Thanks for coming. Good afternoon. So we're talking about network, internet, and our experience on this topic comes from a product that we recently launched. It's called Elk Live. It's basically a solution to do online jamming over the internet. It works at pretty low latency. It currently requires this yellow box that you plug with a wire to your router. It has a convenient web-based interface, very easy to use, plug and play. And we made that with our Elk Audio operating system. You can grab it on elk.audio for Raspberry Pi for free. But anyway, end of the commercial, don't worry. That's not a commercial talk. We don't want to talk about Elk Live, but we want to take advantage of our experience, the challenges we had to face there, and give you a broad overview of what are the various topics. I'm afraid that this is going to be something like a tasting session. You will just get a sample of each topic. We hope to get your appetite rolling, but you will not feel full at the end. That's why ask us questions. We will be available. There's on the Discord, there's a channel with this talk. We will be available today, tomorrow, so feel free to drill us there. Very happy to help you explore the topic. And also, to narrow things down, we cannot talk about all kinds of audio streaming over the internet. So we will not talk about how to play an audio file in a browser, how to do broadcasting. We will restrict to wired use cases, because wireless is completely another story. So what we want to talk about is how to make music together in real time, live jamming, at low latency What is low latency? It depends on the kind of musician you ask. If it's a fusion, rock progressive, you say, oh no, anything more than 5 milliseconds is too much. But if you're an ambient musician, you can probably live with hundreds of milliseconds. And in our case, the average is 30 milliseconds, which is pretty much the same time that the sound waves will take in the non-digital world to travel from one part in the stage to the other end, 10 meters apart. And that's a situation that musicians can adapt to, and they are able to play rhythmically together. So we have Zoom, Skype, Meet. Why can't we use them? The answer should be obvious to anyone here, I assume. Way too much latency. Instead of 30 milliseconds, you typically have something like 200 and above here. And the reason for this latency are multiple. Some sources of latency are in the network. Other sources that are due because very often you don't have a direct connection. Your connection has to go through a relay server that might be very far away. And then you have sources of latency in the device, in the application itself, like analog to digital conversion, operating system buffer, what anyone talks here at ADC. And finally, if the application was not designed in the first place to handle low latency, it's a requirement that it's not easy to retrofit later. So before we move into all the problems of streaming over the internet, we want to see what's the situation on your local network, because there, things work actually pretty well, and have been working well for many years. There's plenty of standards, protocols, and I'm sorry I don't have time to explain all the differences about them. But just to mention that some of them work at the IP level. So they basically send UDP packets on your LAN. Others operate one layer below in the network stack. That's the case, for example, of AVB that uses particular switches to do real-time networking with good guarantees. And they have their strengths. For example, Dante is extremely good at managing, discovering multiple devices in the network. The Dante guys are having another talk here this afternoon, so if you want, you can check that out. Maybe we can only spend a couple of words on AS67, because that's an international standard, non-proprietary, free to use. And it's actually very simple. They didn't reinvent the wheel. They just said, let's take what the protocols are already there, choose those, and this is AS67. So for the transport packetization, you have the real-time protocol, RTP. The encoding of the payload is literally the same PCM that you have in your uncompressed WAV file on the computer. For the synchronization, they use a precise time protocol. All of these have been around before AES-67, quite a long time. And then you have those session protocols. For example, SDP, session description. It's something used to say, I want to stream 48 kilohertz, 16-bit to 2 channels. Or you have a SIP, session initiation. And that's for things like, hey, can I call you? And the other person can reply, no, sorry, now I'm busy. And so you can establish an initial connection. RTP, maybe a couple of more words on it. It usually 99% is implemented over UDP. It's just a very few bytes, additional bytes. And you have a header, typically has some source information. UDP, connectionless, not reliable, unordered. So RTP adds a sequence number so that we can reconstruct this sequence and have the stream in order. We're talking about real-time. Timing information is very important. So there's a timestamp in the packets, a bunch of other stuff we don't care, and finally the payload. The payload does not need to be audio. You can literally have whatever you want. You can stream video, robotics, gaming. And if you use, let's say, an RTP library, the responsibilities of that are pretty small. It helps you to reorder the packet. It gives you source information, who is sending this packet. It can control a little bit the stream and give you statistics, like what is the latency now, how many packets are we dropping, things like that. So I said these things work pretty well in your local network. Can use them in longer distances, let's say one city to another. The answer is yes, but not on your consumer internet. You really need something like a dedicated cable, what is sometimes called dark fiber, and it's a very expensive thing. So unless you're a broadcasting studio or whatever, you would need to find other solution. And now Max will tell you why the internet is so complex.
Yeah, thank you. So indeed, the internet is a very, very, very different beast. And probably the first thing that will bite you is packet loss. Packet drops are a real thing on the internet, a very common thing, actually. They're quite rare, possible, but quite rare on controlled LAN, managed LANs. But on the internet, you're going to get packet drops. And when I say packet drops, it could be proper packet drops, like just disappearing. But it could also be for us audio guys, it could be just packets coming way too late, right? So you're going to have to deal with that, that's for sure. Then, of course, bandwidth becomes an issue. You need to think about bandwidth. Your users will probably have varying amount of available bandwidth. Probably their upstream will be different than downstream. Probably the time of day will affect the performance. All of that needs to be taken into account as well. Latency and jitter, of course, where that's what this talk is really about. On the LAN, it's most of the time predictable, so you can come up with solution. On the internet, I mean, I don't know how to explain. It's just whatever. Synchronization will be tricky on the internet. PTP works very well on LAN, but it's not very good at handling jitter. And so in most cases, on the internet, you need to find another solution. Yeah, encryption, user authentication. You can't go around that on the internet. It's absolutely critical. It needs to be there. On LAN, well, depending on your use case, you might want to have it, but it might be totally irrelevant as well. Another set of things to think about. The last thing is actually connection. It's really not trivial at all. It's actually a pretty hard problem. I mean, not in a mathematical way, but it's tough. And I would like to spend a few more minutes specifically talking about that, how you get two users to connect over the internet. It will probably be a bit too high level for some of you, maybe for all of you, I'm sorry. It's a bit newbie, but it's quite important to understand where the challenge comes from and how we can start addressing them. So the typical typical situation is this, right? We have Alice, we have Bob. They both live on their LAN, their local network, their home router, home LAN. They got their host, their computer got a local IP from the DHCP server in their router, and the router itself has an external facing interface which got a public IP from the ISP, right? I'm gonna go even more noob. I'm sorry for a couple of seconds. I would like to make sure that everyone understands how consumers actually manage to connect to servers on the internet. And it works like this. You have your host, your Alice. They get their local IP, 10.0. You're familiar with those. That lives on a private network. There's the router. The router has a public IP, this 150.150, facing the internet. And there's a server whose public IP is known, whether through DNS or post, whatever. The host wants to connect with the server. It builds a request. In the header, there's going to be a source IP, its own local IP, and the destination IP, the destination of the server. That request is put on the LAN, finds its way to the router, and the router will perform network address translation, or NAT. What it basically means is that it's going to replace the source IP by its own public IP. So the request header becomes this, 150.150.01 for the source IP, and destination IP is the same. That is put on the internet. Eventually, jitter, latency, blah, blah, but eventually it will find its way to the server. The server will process the request and build a response, and the response will basically simply swap source and destination, and the packet is put back on the internet, and eventually, if everything goes well, find its way to the router. The router remembered the translation that it did before, so it's just a matter of swapping the original source IP in the new destination IP field, put that packet on the LAN, and eventually it will find its way back to the host, right? That's very typical. It's been around forever. Everyone should know that, right? Okay. But maybe you see the problem. Already the problem is there, right? In peer-to-peer, how do I find the public IP of the musician, let's say in our case, that I want to connect to? They don't really have one. So if we go back to the first diagram, if Alice wants to talk to Bob, what destination IP can she use? Not Bob's local IP, right? That is meaningless on the internet. The packet will be dropped straight away, probably already by the router. Maybe Bob's public IP? Well, yeah, the packet will find its way to Bob's router, but then the router has no idea what to do with it, right? So it's going to drop it. It doesn't know that it's supposed to go to Bob. It did not perform a translation. It has no concept of that. So that's going to be a big problem. So how do you fix this? Well, maybe some of you remember early online gaming and port forwarding, having to manually configure your router to open ports. Maybe you set up, I don't know, a Minecraft server for your kids a couple of years ago or whatever, and you had to look at the back of your router, log in the configuration page, find port forwarding, and set it all up. What it amounts to really, it's quite straightforward. It's an explicit configuration of your router to tell it whatever packets coming in on a particular specified port, I want you to forward that on the LAN to that particular IP. It works very well. I mean, it did provide quite large amounts of fun back then, but it has limitation. it makes peer-to-peer possible, so I guess it's positive. This configuration, even though it's manual in the case on the screenshot I showed before, there are actually protocols and tools to try to make it more transparent for the users. But they're called UPnP for Universal Plug and Play and NatPMP. But these solutions are not foolproof. And in a lot of cases, you'll have to have your users go into their router, manually configure it. That's something we don't want anyway, where our target is musicians, not network engineers. And that could be a bit scary. So we don't want that. Plus, port forwarding works, but not in all cases. Corporate firewalls, proxies, and things like that will break the system. Also CGNAT, right? CGNAT stands for carrier-grade NAT. It's a flavor of network address translation that ISPs implement over their entire user base. The idea is that they can then save up on IPv4 address space. You know that IPv6, unfortunately, is whatever. But it's crucial for ISPs to save up on addresses, and having this extra layer of address translation allows them to actually use fewer of those. But because this layer of NAT is totally inaccessible for users, the port forwarding technique is impossible to implement. So what do we do? Well, actually, the web industries has solved this problem a long time ago. And the current go-to framework that you would have to look into, for instance, if you want to design an application like Google Meet, for instance, is called WebRTC. WebRTC is a collection of protocols, really, that does way more than fixing our problem of connecting peer-to-peer. It's also browser-centric. So for us, for our product, it's a no-go, of course, and in general for an embedded device, it's a no-go. But still, it was very interesting for us, and anyone wanting to develop that kind of application will have to dive quite deep into the protocols that WebRTC leverages. And these are mainly these three. ICE on the right for interactive connectivity establishment is the main one. It's really the solution. And itself, it leveraged both STUN, which stands for Session Traversal Utility over NAT, for NAT, sorry, and TURN, which is traversal using relay around NAT. A nice excerpt of their respective RFCs. It's a fascinating read, especially if you have trouble sleeping. It's highly recommended, only a couple of 100 pages. But it's probable that just like we did, at some point you will have to dive into those. I'm sorry, but that's just the way it is. It might be interesting to explain a bit deeper how these protocols work and how they fix the problem that we outlined a bit before. It's sometimes referred as UZP hole punching. I don't know if anyone is familiar with this term, hole punching. And basically, it works like that. First, it relies on the existence of a server. Why a server? Well, because we saw before that connecting to server is actually quite easy for even if you're inside a LAN or even inside a layer cake of LANs. And what that server will be used for is that what the protocol calls agent, so Alice, for instance, would send it a stern request, and the server will reply with what's called a connection candidate. A connection candidate is you can see it as basically a reflection of what NAT did to the original packet from Alice. It's basically telling Alice, hey, you know what? Your original packet, actually, your router replaced the destination IP by this IP, your public IP, and is also using this particular port. I didn't go into detail over NAT, but NAT also assigns random ports to the outgoing packets. So now Alice knows that, well, I have this access to myself, right? It's not that easy because, of course, once the response came back, well, the router forgot about this this address translation. So the protocol also asks you to implement techniques to maintain those and refresh those bindings, as it's called. But that's all taken care of by Stun. And then if Bob would do the same, well, both of them now have some sort of address, some sort of location that could be used by anyone else to connect to them. And they could exchange those. They could call each other, send an email or whatever. Hey, you know what? Use this IP address and this port. Right now it's open. It's being maintained by Stun. Try to connect to me, and I could work. Of course, they're not going to call each other or send an email. The top level protocol ICE that I mentioned before takes care of that. That's really what it does. Yeah, she's a candidate. That's really what it does. It's a bit more complex now. You have the Stun server, but you also have a messaging server that you need to deploy. That server will be used for these exchange of candidates and a bunch of other stuff. There's handshaking going on. There, session description SDP is used to describe sessions. There's actually a collection of candidates that you get from Stun. Stun will most likely give you at least two candidates, an IPv4 candidate, an IPv6 candidate as well. It will also produce a host candidate if we are inside a LAN. So each agent will actually have a list of candidates, and ICE will determine how these will be paired and how they will be tested. Each pair will be tested to see if the connection actually happens. And then once a connection is established, the protocol also defines how the agents will elect one, settle on it, and then close the protocol, the handshaking when the session is actually going. So for ICE, this is what for peer-to-peer connection, this is basically what we had to do, what you would probably have to do as well. Come up with a Stun server, a turn server. I didn't mention a turn server. Sorry, I forgot that. But there's another server here, which is basically a fallback to Stun. Stun is very reliable, but it doesn't work every time. Again, corporate networks, corporate firewalls, proxies, and things like that will break that system as well. And the fallback is turn. And the basic idea is that we will use a server to relay the packet. So it's not peer-to-peer anymore. I'll touch on that again a bit later, but that's an integral part of the ICE protocol. Yeah, so that's basically the flow. Agents gather their own candidates through Stun. They exchange those. They test the different pairs of possible candidates, and then they agree on a working pair. And now communication can start. We assumed that we want peer-to-peer, right? But it's not obvious. There are other topologies. Peer-to-peer, of course, will be best for latency. Will probably be fewer hops, and it's going to go faster. But obviously, bandwidth will probably be a problem if you increase the size of the number of connection. You end up with a full graph like this, so you can imagine that very quickly, especially with consumer connection, you will reach your bandwidth limit. And as I mentioned, it's not always possible. Turn or relaying server in general is a good fallback. Bandwidth requirement will be lower, obviously, because this time each agent needs to upload their audio only once to the server, which will then echo them, forward them back to to the other agents. Connecting is easier because it's a server on the internet with a public IP. But obviously, you'll add latency, and there's a bunch of other problems that will show up, like coverage, for instance, right? These servers cannot be physically, geographically far from your users, otherwise, well. So how do you spawn these servers close to your user and stuff? That's a whole problem. We're not gonna go into that at all, but you'll be faced with that. And another flavor of this relaying server is a mixing server. It's actually a very interesting area where the server not only forwards packets, but actually does the mixing internally. So all the agents send their audio to the server. You need to come up with a clever remote controlling scheme, application, whatever, to allow each agent to fine-tune their mix of all the others. The mixing server builds the mix and sends it back as one stream to the user. It's the lowest bandwidth requirement, obviously, but you will be faced with the same challenges as with the relaying server. I think I've spoke enough about protocols. It can be pretty boring. It's time to look at software now, I think. Stefano?
Yeah, thanks. So yeah, now we're assuming the connection is established. We don't care anymore about that. What we want to see is how we can get a good quality stream. So imagine you're writing C++ application. First thing you're going to need, guess what? Network thread. You need to receive the packets and do some stuff on them. We said reordering, one. Number two, very important, you need a jitter buffer because the latency is not always going to be the same and you need to compensate for that. And this is a natural compromise between latency and quality. If you want the best quality, you need a large buffer. If you want the lowest latency, you need a smaller buffer. Then you have your old good friend, the real-time audio thread connected to the operating system, callback. The first thing it does, it pulls data from the jitter buffer. This data is typically encoded in a way during the transport, and it's not the same format that the operating system needs. So you need to decode the data. You can use PCM. Some perceptual codecs are good or can be used. For example, the Opus codec is used by Google Meet and those kind of WebRTC frameworks. It's non-proprietary, free to use. There are other new codecs like LC3+, pretty interesting, can operate up down to 5 millisecond latency, and it's designed to be full bandwidth, not just for speech. And you pull data if you have data, because if you're unlucky, you cannot wait for packets. We need to do something, give audio to the sound card. And if you don't have data, well, we have to invent it. And we have to do it in a way that we try to mask, conceal the error. So at least what we want is that the user doesn't hear an audio glitch. And finally, we already mentioned same problem as in the local network. Different devices, you need to synchronize them. And then you're ready to send the audio out. So this is a consuming stream. You get packets, you produce audio. In the other direction, things are much simpler. You get your data, your audio from the sound card, you encode it, and bam, you send it out as fast as possible. That's pretty much the end of the story. And the full duplex application is kind of the combination of the two independent streams. Sometimes there are some interconnection, but you can think of in this way. So many enemies that we have to deal with. Enemy number one, latency, and its sibling, jitter. When we think about network latency, you probably think about this. You ping a server, you get various lines. Every line tells you, okay, now latency is 12 milliseconds, then 14, and you stop ping, you get some summary. This should tell you one important thing. Latency is not a number, it's a statistical distribution. Those lines, you can think of them as samples of that statistical distribution. However, the summary that pings gives you is quite limited. You have minimum, maximum, average, standard deviation. By the way, this standard deviation is probably the most used definition of jitter, one of the most common. And looking at these numbers, one might think that the histogram, the distribution of latency, could look like this. You have a narrow normal curve centered around one latency value, sometimes a little bit later, sometimes a little bit faster. Well, it would be nice if in the internet would be like that. If you actually measure it over the internet, you're more likely to see something like this. So in the majority of the cases, like the mode value here, the blue line, you get data when you expect it. If you're lucky, in a smaller percentage of the cases, you get data even a little bit earlier. But then you can have a lot of variation in the delay you can achieve. And sometimes packets are totally lost. So our jitter buffer basically gives us a time window. So starting from that moment that we expect to receive packets, we basically get a maximum allowed time. And any packet that we receive later than that time, for us, is completely lost. So it doesn't matter if it eventually arrives. For us, a dropped packet is a packet that arrives after the end of the jitter buffer window. Latency measurement, these histograms are actually pretty important. You should do a continuous measurement in your software to be up to date, see what is the situation in the network right now. There are various algorithms. For example, we do this measurement online using the same stream that we use for the audio. The idea is like this. So Alice is sending packet 66. We know we have the sequence numbers, the tags. And when it sends this packet, it takes a timestamp. She saves the timestamp. And when Bob eventually receives the packet, in that moment, Bob is sending his own packet with his own sequence number to Alice, let's say 77, and it has another information, a reply tag, like, you know what, in this moment, I saw your packet 66. And when Alice receives this, she takes another timestamp, takes a difference, and now she has not the full histogram, one sample of the histogram. Then a lot of smoothing, a lot of filtering, but you get those fancy diagrams. And they're not just useful to make slides in the presentation. Actually, having that histogram can be useful to make the life of your user easy. Because remember the question, how big should be the jitter buffer? Well, one solution is, we don't care, let the user care about it, give them a control, a slider, but you probably don't want while you're playing, oh, sorry, let's change the buffer and so on. It's much better if we do statistical analysis. For example, we can look at the percentile, we can look at various things like package operation, and we can try to adjust the jitter buffer so that the user doesn't have to care about it and things just work. Okay, very quickly about the time synchronization problem for the machine, for the devices. We said it's all about clocks. You have different clocks. The clocks have different speed. They refer to different clocks domain. You have a network time, you have a local audio time connected to the codec, to the CPU. And even if you synchronize the clock at the beginning, the clock have a slightly different speed. So actually, we tried, if you disable clock synchronization, you can play for maybe, I don't know, 4 or 5 minutes, 10 minutes, depending on the case. After that, what happens is that one clock is going to be later, and then the packets will be late. The jitter buffer will be filled. All you hear are just glitches. I'm not going to tell you more about it because Fabian Rangils, which I think is also here, gave an excellent talk last year here at EDC. And I highly recommend to check it out. Even if it was focusing on another use case mostly, synchronizing clocks on a single device, one of the solutions he was proposing, asynchronous sample rate conversion, works very well here as well. Then if you're lucky, if you have, for example, very good corporate subnet part of the internet, you can use PTP. Or if you have access to GPS, that's the same GPS you use for Google Maps on your phone. That's actually another solution because GPS satellites, they have a very accurate word clock. It's the same for everyone. But if you're on a device inside the building, not always possible. And finally, it's also possible if you have some assumption on your packet format and size to do some statistical analysis and try to deduce when this drift is happening and do some kind of small skipping of the jitter buffer. So you kind of, okay, I'm late, let's jump time ahead. You're going to introduce theoretically a small audio glitch, but it can be smoothed out. If you do things properly, users won't hear it. So not only the machines need synchronization, also humans, and they need to play on the beat together. And musician, just a reminder for everyone, latency exists in the non-digital worlds as well. And if you think about orchestra, the elements of the orchestra are pretty far away, a large orchestra. And they can have like even 20 or more milliseconds of audio latency, even 30, 40. And they are able, and the latency varies for all the elements, but they're able to play on time, right? And even musicians on smaller spaces, like on a stage, they actually play with latency. Think about your guitar player. You want to hear your signal, your monitor signal coming from the amplifier, very close, very quick. You stay close to the amplifier. But then you play with the bass player, and it happens that you move away from the amplifier. You're basically increasing your own monitor latency, but you're getting closer to the other musician. And playing together is actually a human feedback loop. So musicians adjust, they start to play a little bit in advance until they phase lock and they can play their nice, tight, funky music or whatever together. And in a digital system, we can try to do something similar. It's a very simple idea. But basically, you will have always your own monitoring delay, typically pretty small, and the delay of the other source is going to be much larger. If you're monitoring yourself with closed-back headphones, then we can think of increasing your own monitoring delay in the same way as that guitar player was moving away from the amplifier. And the idea is that you're adding something to yourself, but it's easier for you to play on the beat with the other person. So how much should this delay be? Well, we can measure it, right? We can measure the latency, so we can match things so that it can happen exactly at the same time. We actually found out it's actually a very personal matter, because some musicians, like singers, they don't like monitoring delay at all. Other musicians, they do want it. And a continuous slider works pretty well, and you can also do fancier things than just a delay, do some signal processing there, but that's the idea. So enemy number 2, I guess the final boss, packet drops. And the first weapon we have to fight packet drops is make our stream more robust, so we can add redundancy to the stream. There's also implemented many years ago, it's called the redundant audio data RED. So the idea is that in your RTP payload, you put your last packet available, best quality, and if you still have room in your UDP packet, what you can do is put some replicas of previous packets, and if you want to maximize redundancy, you don't have to use the best quality for those replicas. For example, you can use 8-bit reduced sample rate, and this thing works because we have the jitter buffer. So let's say that Alice is sending packet 144 to Bob. The network is good. Bob receives the packet, puts it into the jitter buffer. Then the audio interrupt clicks on Bob, and Alice is sending another packet, 145. This gets lost on the internet, and now Bob has a gap in the jitter buffer. Still, the user hasn't heard the glitch because we are still consuming previously entry in the jitter. Now, luckily, the next packet arrives in time, and it has the information needed to reconstruct 145, just exactly one interrupt before Bob needs to pull the data. So, no glitch, all good. This works under certain conditions. So it's best when you have a small payload in time for the packets, when you have a long jitter buffer, which is not ideal, and when you're not losing too many packets, the burst of packet is short. Because if you're dropping 20 packets in a row, you probably don't have enough redundancy to reconstruct them. So if that happens, you tried everything, you're still losing packet, we said, let's do something, let's invent some data. The goal here, again, is minimize the audible glitches. So if these things happen for a short period, hopefully the user won't hear anything. There are some rules to this game. Rule number 1, only zero latency algorithms. The reason is, if you're going to add latency in your algorithm, you might just as well increase the size of the jitter buffer. You're probably going to get the same results in a much simpler way. Rule number 2, you can only reconstruct and predict the steady state evolution, but you cannot recover the transients. Because even if that was possible, then you're replacing the intention of the musician. Replacing transient means you're playing a new note for the musician. So this only works to predict periodic evolving signals. And at the signal level can look something like this. So this is like, let's say, the waveform that Bob is receiving, one packet at a time. When the situation is good, you get this periodic waveform. We get in packet, all good, second packet good, third good, and then bam. We don't have the data. If we don't do anything, we don't put either silence or noise, a glitch is going to be heard. And this is classic signal processing problem. You can do prediction technique like linear prediction, whatever. And you can try to find a waveform that follows the previous data. Maybe it's not as accurate. Like here, you have less harmonics than the original signal, but at least it will probably not be heard by Bob. And then, if you get valid data, you still don't want to immediately switch to a new stream. You're going to do some cross-fading between the original and the new one. So the algorithm is like this. So you have this switch, and if things are good, you just stream packets, you save them in the file file, you save the history, and you use the history to train a predictor. Things go bad, use the predictor, you crossfade. Crossfade is not as trivial as it might seem, because you can do equal amplitude, equal power. The optimal way to do crossfading here is quite tricky. There are many algorithms. The difference between them is just about the predictor technique. The simplest one are sample-based. You can use, for example, linear prediction. Let's use the Opus. When you hear someone with a sign-like voice, Google Meet, that's typically what's happening. You can use more computational intensive, but more accurate algorithm that works on larger block of signals, like the Burke's method. That's what we use in ArcLive. And these days, deep learning, neural networks, we start to see something like that. So Google is employing machine learning technique in WaveNet Duo for speech conferencing. There is some research going on for musical signal, but if you have to do the training and thing working for any kind of musical signal, it's a much harder problem than just making it work for speech. There's a nice DAFX article that compares the old school methods, if you want to check it out. But I guess that was it. There's a lot of new things, but we would like to stop here. Maybe have more times for questions. And thank you.
Fantastic. Thank you so much.